Hello, everyone. My name is Batel Gabay. I'm a master's student in Tel Aviv University in Environmental Bioengineering Lab. In this presentation, I'm going to talk about the detection of brain melanoma using innovative biopsy technique termed E-biopsy. A major concern in tissue biopsies with a needle is missing the most lethal clone of a tumor, leading to a false negative result. Needle-based biopsies gather tissue information limited to the needle size. In this work, we present E-biopsy, a minimally invasive technique which enables molecular harvesting using electroporation. This study suggests that E-biopsy could increase the sample tissue volume in comparison to tissue sampling by a needle alone. Here, E-biopsy method is presented. First, needles are inserted into the intake tissue. Here is the needle electrode in red, and here is the ground electrode in black. Then pulse electric fields are applied to permeabilize the cell membrane. Second, vacuum is applied on the needle to extract the cellular content. Third, the tissue extract is discharged from the syringe to the external buffer and subjected to standard protocols for molecular analysis. To study the distribution of the electric field in the brain tissue at different positions of the needle, we perform numerical simulations of the electric field in 3 scenarios. So the black circle is the melanoma tumor, the blue is the ground radius, and the green is the E-biopsy needle radius. In model A, E-biopsy sampling electrode is in the middle of the visible tumor in the center. In model B, the electrode is near the visible tumor margins. And in model C, the electrode is far away from the tumor in the healthy brain tissue. To model the distribution of the electric field and brain and melanoma tumor during E-biopsy, we use the finite element method, which allows us to find an approximate solution in complex geometries. We solve Laplace equation with boundary conditions defined by the applied voltage. So first short high voltage pulse, followed by long low voltage pulse. The simulation results of the electric field distribution during E-biopsy are presented. We assume the thermal properties of the mice brain didn't change after electroporation, while the electric conductivity after electroporation increased. The left set of models show the electric field distribution at early stages of the electroporation, with lower conductivities of the melanoma and healthy brain tissue. Right panel show the electric field distribution at late stages of electroporation when the tissue conductivity increases. As the extent of cell permeabilization by pulse electric field depends on the electric field strength, we highlighted the areas of the brain that are exposed to electric fields higher than 700 volt per centimeters, and areas that are exposed to electric fields higher than 500 volt per centimeters. These threshold values have been reported in the literature as thresholds for irreversible and reversible electroporation of the brain. The application of electric fields on tissue could lead to heat generation by Joule heating. Here is the equation we use to calculate the power supplied by the pulse electric fields. For the thermal distribution, we solve the transient heat transfer equation. Heat sources were imported from DC conduction and steady-state heat transfer problems coupling for the thermal field problem. Both high voltage short pulse duration and low voltage long pulse duration lead to tissue heating. Simulation results for this protocol are presented in panels A until C. Panels D until F show the temperature change as function of distance from the electrode over the contour. This is the contour. Panels G until I show the temperature changes as function of time at the highest temperature points over the contours located 0.158 millimeters in model A, 0.144 millimeters in B, and 0.123 millimeters in model C. I want to repeat the performed simulations using the software. So first, the short duration high voltage protocol is applied. As mentioned, we first solved the DC conduction problem. So I need to DC conduction. This is the DC conduction problem. Wait, we need to do like this. Okay. So I want to show you. Okay. So we use the VRMS calculated volume, in this case 12.65 volt. And let's solve. So it's loading the model. Then we couple steady state heat transfer with the Dirichlet boundary condition. Steady state. So the temperature is constant with time. This is the airline. The temperature of the airline is 25 Celsius, and it differentiates between the mouth brain tissue and the air. Then heat sources were imported from DC conduction problem and steady state heat transfer problem we solved for the thermal field problem. So here is the transient heat transfer problem. We link a DC conduction problem and the steady state heat transfer problem, all with the same geometries. And we pulse for 10 seconds, that's all. Okay, so if you want to see what happens in the first 10 seconds, we can draw a line using contour application from the electrode. We assume that this is where the highest temperature. Then we can see here, for example, the temperature as function of the distance from the electrode. Okay, and then we can see where is the highest temperature. So we found it. And we can see what happens in this location over time. So we can see in 10 seconds, 8, etc. Then we move to the long duration low voltage protocol. We solve another DC conduction problem with calculated VRMS volt, 10 volts. That's all. They're similar, those problems. And we couple it with the former transient heat transfer problem. This is the next one. We link DC conduction problem and the former transient heat transfer problem, starting from 10 seconds after the pulse end. Let's solve. So the total pulsing time is 20 seconds. We can draw the exact same line in the exact same location. This is how we can extend our results for 20 seconds. Okay, so let's get back to the presentation. These simulations allow us to get an initial understanding of tissue areas from which e-biopsy could potentially collect the intracellular molecular markers released by electroporation. If the electric field strength thresholds for the tissue are known, the developed simulation could indicate the fraction of tumors that are electropermeabilized using this equation: visible tumor coverage. As seen in the table, when the needle was inside the tumor in model A, the electroporated area was larger. The tumor tissue is electroporated also in model B, although the needle is positioned outside of the tumor. That allows us the detection of tumor presence. We calculated the tumor area using contour application in QuickField. So e-biopsy differentiates between melanoma tumor and healthy brain in mice. We demonstrated e-biopsy could provide a possibility to detect tumor margins or detect tumor presence near the biopsy needle, with the potential to reduce false negative results of needle biopsies. So these pivotal findings were corroborated with numerical model, which serves as first estimation of the sample tissue areas using e-biopsy. Thank you very much.